Hi. Welcome to this week's edition of Cosmology. Without further ado, let's get started. Biological considerations. Habitability. There may be scientific support, based on studies reported in March 2020, for considering that parts of the planet Mercury may have been habitable, and perhaps that life forms, albeit likely primitive microorganisms, may have existed on the planet. Observation. Mercury's apparent magnitude is calculated to vary between -2.48 around superior conjunction and 7.25 around inferior conjunction. The mean apparent magnitude is 0.23, while the standard deviation of 1.78 is the largest of any planet. The mean apparent magnitude at superior conjunction is -1.89, while that at inferior conjunction is 5.93. Observation of Mercury is complicated by its proximity to the Sun, as it is lost in the Sun's glare for much of the time. Mercury can be observed for only a brief period during either morning or evening twilight. Mercury can, like several other planets and the brightest stars, be seen during a total solar eclipse. Like the Moon and Venus, Mercury exhibits phases as seen from Earth. It is new at inferior conjunction and full at superior conjunction. The planet is rendered invisible from Earth on both of these occasions because of its being obscured by the Sun, except its new phase during a transit. Mercury is technically brightest as seen from Earth when it is at a full phase. Although Mercury is farthest from Earth when it is full, the greater illuminated area that is visible and the opposition brightness surge more than compensates for the distance. The opposite is true for Venus, which appears brightest when it is a crescent, because it is much closer to Earth than when gibbous. Nonetheless, the brightest appearance of Mercury is an essentially impossible time for practical observation, because of the extreme proximity of the Sun. Mercury is best observed at the first and last quarter, although they are phases of lesser brightness. The first and last quarter phases occur at greatest elongation east and west of the Sun, respectively. At both of these times Mercury's separation from the Sun ranges anywhere from 17.9 degrees at perihelion to 27.8 degrees at aphelion. At greatest western elongation, Mercury rises at its earliest before sunrise, and at greatest eastern elongation, it sets at its latest after sunset. Mercury can be easily seen from the tropics and subtropics more than from higher latitudes. Viewed from low latitudes and at the right times of year, the ecliptic intersects the horizon at a steep angle. Mercury is 10 degrees above the horizon when the planet appears directly above the Sun and is at maximum elongation from the Sun, and also when the Sun is 18 degrees below the horizon, so the sky is just completely dark. This angle is the maximum altitude at which Mercury is visible in a completely dark sky. At middle latitudes, Mercury is more often and easily visible from the southern hemisphere than from the northern. This is because Mercury's maximum western elongation occurs only during early autumn in the southern hemisphere, whereas its greatest eastern elongation happens only during late winter in the southern hemisphere. In both of these cases, the angle at which the planet's orbit intersects the horizon is maximized, allowing it to rise several hours before sunrise in the former instance and not set until several hours after sundown in the latter from southern mid-latitudes, such as Argentina and South Africa. An alternate method for viewing Mercury involves observing the planet during daylight hours when conditions are clear, ideally when it is at its greatest elongation. This allows the planet to be found easily, even when using telescopes with 8 cm apertures. Care must be taken to ensure the instrument isn't pointed directly towards the Sun because of the risk for eye damage. This method bypasses the limitation of twilight observing when the ecliptic is located at a low elevation. Ground-based telescope observations of Mercury reveal only an illuminated partial disk with limited detail. The first of 2 spacecraft to visit the planet was Mariner 10, which mapped about 45% of its surface from 1974 to 1975. The second is the Messenger spacecraft, which after 3 Mercury flybys between 2008 and 2009, attained orbit around Mercury on March 17, 2011, to study and map the rest of the planet. The Hubble Space Telescope cannot observe Mercury at all, due to safety procedures that prevent its pointing too close to the Sun. Because the shift of 0.15 revolutions in a year makes up a 7-year cycle, in the 7th year Mercury follows almost exactly the sequence of phenomena it showed 7 years before. Ground-based telescopic research. The first telescopic observations of Mercury were made by Galileo in the early 17th century. Although he observed phases when he looked at Venus, his telescope was not powerful enough to see the phases of Mercury. In 1631, Pierre Gassendi made the first telescopic observations of the transit of a planet across the Sun when he saw a transit of Mercury predicted by Johannes Kepler. In 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. The observation demonstrated conclusively that Mercury orbited around the Sun. A rare event in astronomy is the passage of one planet in front of another, as seen from Earth. Mercury and Venus occult each other every few centuries, and the event of May 28, 1737 is the only one historically observed, having been seen by John Bevis at the Royal Greenwich Observatory. The next occultation of Mercury by Venus will be on December 3, 2133. The difficulties inherent in observing Mercury mean that it has been far less studied than the other planets. In 1800, Johann Schroeder made observations of surface features, claiming to have observed 20-kilometer high mountains. Friedrich Bessel used Schroeder's drawings to erroneously estimate the rotation period as 24 hours and an axial tilt of 70 degrees. In the 1880s, Giovanni Schiaparelli mapped the planet more accurately, and suggested that Mercury's rotational period was 88 days, the same as its orbital period due to tidal locking. This phenomenon is known as synchronous rotation. The effort to map the surface of Mercury was continued by Eugenio Antoniadi, who published a book in 1934 that included both maps and his own observations. Many of the planet's surface features, particularly the albedo features, take their names from Antoniadi's map. In June 1962, Soviet scientists at the Institute of Radio Engineering and Electronics of the USSR Academy of Sciences, led by Vladimir Kotelnikov, became the first to bounce a radar signal off Mercury and receive it, starting radar observations of the planet. 3 years later, radar observations by Americans Gordon H. Pettingill and Rolf B. Dice, using the 300-meter Arecibo Observatory radio telescope in Puerto Rico, showed conclusively that the planet's rotational period was about 59 days. The theory that Mercury's rotation was synchronous had become widely held, and it was a surprise to astronomers when these radio observations were announced. If Mercury were tidally locked, its dark face would be extremely cold, but measurements of radio emission revealed that it was much hotter than expected. Astronomers were reluctant to drop the synchronous rotation theory and proposed alternative mechanisms such as powerful heat-distributing winds to explain the observations. Italian astronomer Giuseppe Colombo noted that the rotation value was about 2/3 of Mercury's orbital period, and proposed that the planet's orbital and rotational periods were locked into a 3:2 rather than a 1:1 resonance. Data from Mariner 10 subsequently confirmed this view. This means that Schiaparelli's and Antoniadi's maps were not wrong. Instead, the astronomers saw the same features during every second orbit and recorded them, but disregarded those seen in the meantime, when Mercury's other face was toward the Sun, because the orbital geometry meant that these observations were made under poor viewing conditions. Ground-based optical observations did not shed much further light on Mercury, but radio astronomers using interferometry at microwave wavelengths, a technique that enables removal of the solar radiation, were able to discern physical and chemical characteristics of the subsurface layers to a depth of several meters. Not until the first space probe flew past Mercury did many of its most fundamental morphological properties become known. Moreover, recent technological advances have led to improved ground-based observations. In 2000, high-resolution Lucky imaging observations were conducted by the Mount Wilson Observatory 1.5-meter Hale telescope. They provided the first views that resolved surface features on the parts of Mercury that were not imaged in the Mariner 10 mission. Most of the planet has been mapped by the Arecibo radar telescope, with 5 km resolution, including polar deposits in shadowed craters of what may be water ice. Research with space probes. Reaching Mercury from Earth poses significant technical challenges, because it orbits so much closer to the Sun than Earth. A Mercury-bound spacecraft launched from Earth must travel over 91 million kilometers into the Sun's gravitational potential well. Mercury has an orbital speed of 48 kilometers per second, whereas Earth's orbital speed is 30 kilometers per second. Therefore, the spacecraft must make a large change in velocity to enter a Hohmann transfer orbit that passes near Mercury, as compared to the delta V required for other planetary missions. The potential energy liberated by moving down the Sun's potential well becomes kinetic energy, requiring another large delta V change to do anything other than rapidly pass by Mercury. To land safely or enter a stable orbit, the spacecraft would rely entirely on rocket motors. Aerobraking is ruled out because Mercury has a negligible atmosphere. A trip to Mercury requires more rocket fuel than that required to escape the solar system completely. As a result, only 2 space probes have visited it so far. A proposed alternative approach would use a solar sail to attain a Mercury synchronous orbit around the Sun. Mariner 10. The first spacecraft to visit Mercury was NASA's Mariner 10. The spacecraft used the gravity of Venus to adjust its orbital velocity so that it could approach Mercury, making it both the first spacecraft to use this gravitational slingshot effect and the first NASA mission to visit multiple planets. Mariner 10 provided the first close-up images of Mercury's surface, which immediately showed its heavily cratered nature, and revealed many other types of geological features, such as the giant scarps that were later ascribed to the effect of the planet shrinking slightly as its iron core cools. Unfortunately, the same face of the planet was lit at each of Mariner 10's close approaches. This made close observation of both sides of the planet impossible, and resulted in the mapping of less than 45% of the planet's surface. The spacecraft made 3 close approaches to Mercury, the closest of which took it to within 327 kilometers of the surface. At the first close approach, instruments detected a magnetic field. To the great surprise of planetary geologists, Mercury's rotation was expected to be much too slow to generate a significant dynamo effect. The second close approach was primarily used for imaging, but at the third approach, extensive magnetic data were obtained. The data revealed that the planet's magnetic field is much like Earth's, which deflects the solar wind around the planet. For many years after the Mariner 10 encounters, the origin of Mercury's magnetic field remained the subject of several competing theories. On March 24, 1975, just 8 days after its final close approach, Mariner 10 ran out of fuel. Because its orbit could no longer be accurately controlled, mission controllers instructed the probe to shut down. Mariner 10 is thought to be still orbiting the Sun, passing close to Mercury every few months. Thank you for watching this video. If you liked this, please give it a thumbs up and subscribe for more such contents.